Did anyone try to see that the inverse Fourier series, I mean this is called inverse Fourier series. You remember one of the examples we worked out was, I mean still there are how many, 3 people are still missing. So maybe, okay, let me just start just reminding you this example that we did. So the example was f of theta was 0 and 1. So the range was between 0 to pi, and here it was minus pi. So this was a function, and so this function was is discontinuous, as you can see. I mean, if you try to plot it, this function is between minus pi and pi. Here is 0. So in this region, f is 1, and there it is 0. So f looks like this. It's a step. It's a kind of a step function, and we worked out the Fourier series of this. So Fourier series, of course, is simply defined by f theta 1 over root 2 pi, f theta e to the minus im theta d theta from minus pi to pi, right? And we worked out this explicitly, and the answer was f0 was 1 over 2. I mean, there is a 1 over root 2 pi anyway, and 1/2. Is that correct? No, pi by 2. Sorry, pi by 2, right? Because for m equal to 0, it's just the integral of f, right? Where integral of f, you are just integrating from here to here because there it is 0. So in this part, it just gives you the pi. So pi, pi, simply pi. So that's f0, and fm was fm was I over m root 2 pi times 1 minus 1 to the m. This was this was fm. I mean, this was, we worked it out explicitly. Just you have to integrate it, right? I mean, again, the integral will just go from minus pi to 0, because from 0 to pi f is 0. So we just have to integrate e to the minus im theta from minus pi to 0, and you get this answer. Okay. So then now, so let's consider the sum fm e to the power of im theta summed over m, 1 over root 2 pi of that. The question is does it give you back the f theta or not? Because remember, this is supposed to give you 1/2 of f theta plus 0 plus f theta minus 0, right? This is what the theorem says. It should give you that. And indeed, we checked. So I mean, this is for m not equal to 0. This one, that's f0. Here, this is sum is over everything. So you can see that this object is nothing else but pi. I think 1 over root 2 pi. So pi by 2, correct? I mean, there is a 1 over root 2 pi, so that makes it pi by 2. Plus all of this, which is plus I over 2 pi m 1 minus 1 to the m e to the I m theta summed over m not equal to 0, right? So this is the left hand side. So question is whether this gives you back that answer, right? And indeed, we checked. I mean, this you can simplify this a little bit, because I mean, so sorry, there is an m here. M is inside here. So this, first of all, this tells you that this vanishes when m is even, right? When m is even, this cancels with that, right? So only the odd terms survive. And secondly, you can combine the m positive and m negative, right? Let's say plus 3 and minus 3. Say, for example, m equal to plus 3 and m equal to minus 3. this will just change the sign. One term will be to the I 3 theta, other will be to the minus I 3 theta. But this m also changes the sign. So when you add that up, it will be a difference of these two phases, right? I mean, you see what I'm saying. This object gives you, so for example, let's say m equal to 1. So this gives you a factor of 2. So I can cancel that. So I over pi for m odd they add up, right? So that's so only the odd guy. So for example, e to the I theta for m equal to 1 plus e to the minus I theta divided by minus 1. This is m equal to 1 and m equal to minus 1. Similarly, you have m equal to 3 theta, m equal to 3 will be divided by 3 plus e to the minus I 3 theta minus 3, right? This is m equal to 3 and that's m equal to minus 3 and so on. But then you see that there's a minus sign here. So this gives you e to the I theta minus e to the minus I theta, which is 2i sine theta, right? So you get here, so this is nothing else but 2i sine theta. This guy is again, you see, it's this is 1/3 times 2i sine 3 theta, etc. Right? So the upshot is that this whole thing, I mean, this equation left hand side becomes this plus there is a I here, and okay, there's no, sorry, there is this I and I, so minus 2 over pi. So this gives you minus 2 over pi times sine m theta divided by m. But now the sum is m positive and m odd, right? Because I have taken into account positive and negative together. So now I just have to sum over m, or m positive. So is that correct? Yeah, minus 2 over pi sine m theta. Okay, so this is the left hand side. Okay, and we checked last time that indeed it gives you the correct answer for theta equal to 0 and theta equal to pi. I mean, at theta equal to 0 and pi, it agrees with the right hand side. So for example, at theta equal to 0, I mean, all of these terms disappear because sine of 0 is 0. So you just get pi by 2. Sorry, why is there a pi by 2? No, this pi must cancel. No, there's no pi here. I mean, root 2 pi and a pi here, right? And there is a root 2 pi. So in fact, it's 1/2, correct? So this is 1/2. Yeah. I mean, this root, there is a, if you look at this f0 term, this times 1 over root 2 pi gives you 1 over 2 pi times pi. So pi cancels. So it's just 1/2. So you see that theta equal to 0 and theta equal to pi, the left hand side simply gives you half, okay, which is indeed the correct answer, because the right hand side also gives you the same, because if you look at theta equal to 0, as you come from here, the limiting value is 0. As you come from here, the limiting value is 1. So 1 plus 0 divided by 2, which is 1/2, right? Same way at theta equal to pi, I mean, at theta equal to pi, the relation was 1/2 of f pi plus f minus pi, right? So f of pi is 0, f of minus pi is 1. Again, average is half. So this indeed agrees, right? But this must be true at all values of theta. This must be equal to that. You see, so now if you take any point here, this is here the function is continuous, right? I mean, f of theta plus 0 is the same as f of theta. Take any value theta here. So whether you come from here or come from there, the limiting value of the function is the same, which is 0, right? So this whole expression for theta positive, it must just give you 0, right? Whereas theta negative, some point here between minus pi and 0, some point here, the answer should be 1. Okay. So how can one prove that? That was one question. Let's try to see if we can try to prove this statement. So I mean, one would like to, I mean, actually already let me go back here. I mean, one doesn't have to use this here. So I mean, this expression, let's look at this part here. Okay, this sum. So this sum is 2i over 2 pi, so I over pi, and then you have e to the power of I m theta divided by m, where I'm summing over m odd, both positive and negative, right? M is odd because this gives you 0 for m e1, right? And for m odd, it gives you a factor of 2. So I've taken into account this 2. Okay. So what we want to show is that for theta positive, so theta strictly greater than 0 and strictly less than pi. So it's somewhere in between, not at the end points, but somewhere in between. Okay. This must give you 1/2, right? So that it will cancel with this. It will this should give you minus 1/2. Okay. So that adding, I was saying this part should give you minus half, so that it will cancel with this, and then because your answer should be 0, right? On the other hand, so this answer should be minus half, but on the other hand, if you take the other region, so minus pi strictly, theta is between strictly in this inside somewhere here, then it should add up, right? So in that case, the answer should be 1/2 rather than minus 1/2. Okay, this is what we want to prove. Okay, independent of theta. It doesn't matter which point you choose here; it should always be minus half. Similarly, it doesn't matter which point you choose here; it should be always plus half, right? Which looks a bit strange because there is explicit theta appearing here. How is it possible? How can how can this suddenly the dependence on theta disappear, right? It looks very surprising, but we can try to sum this up. So let's see. We want, again using the residue contour integrals. No, that is a standard trick that we try to use. So let us consider first of all this region. So first of all, let's see what kind of a function would give you poles at odd integers. Okay. So for example, let's consider this 1 over e to the I pi z plus 1. Okay. Consider this function. Okay. So you see that when z is odd integer, this becomes a minus 1, so it blows up, right? But when z is an even integer, it doesn't blow up because it just adds up. So it's a perfectly regular at z equal to e1. But at z equal to odd, there are poles, right? So it is natural then to reproduce this integral as some kind of a contour integral of this function. Not just this function multiplied by some suitable other function, so that we get exactly this residue. Okay. Now, so what should I want? The residue better be this whole thing, right? At z equal to odd integer, if you want. So let's consider. So let's expand this z equal to m plus z prime. So we want to look at z near m where m is odd, because we want to consider what is the residue and what is the Laurent coefficient d minus 1. Okay, so we want to expand z equal to m plus z prime, right? Z prime is small, m is odd. In that case, this expression becomes e to the power, so 1 over e to the I pi m times e to the I pi z prime, but z prime is small, so I can expand. So 1 plus I pi z prime and so on, right? Sign expand. The exponential expansion of exponential. Okay, and then I have a plus 1 here. But if m is odd, this is minus 1, right? So this becomes minus 1. So minus 1 cancels with a plus 1 as expected, because we should have a pole. And what we find that this behaves like minus 1 over I pi z prime, the leading term. That's a leading singularity term. Plus regular terms. But the singularity is this. Okay. So this, I have this one here, and I want to now reproduce the full residue here. It should be this. So then, I'm just going through some examples like this. So today, what I decided that instead of going ahead and trying to complete this chapter, which I could in principle, but there's not much left. But I thought I will just slow down a little bit and try to work out several examples. which will give you some experience of how to use the contour integrals. And then maybe next time I can finish this chapter. Okay. So I want to reproduce this. So let us see what kind of a function we can write. Well, you see, at the m is the position of the pole, right? So I must have something like e to the power of I z theta, right? So that when I write z equal to m plus z prime, then this will just give you e to the I m theta plus regular terms in z prime. I mean expansion z prime, right? So that should be there. There is a 1 over m. So there should be a z here, right? Because again, you see, you get the 1 over m from there. And then, of course, I have this object, 1 over e to the I pi z plus 1. Okay. But this gives me, we said this gives you in the limit, I mean near z equal to m, this gives you minus 1 over I pi z prime. Whereas all those things simply give you, the leading term is simply e to the I m theta over m. Okay. Now there are these things I by pi. So that in fact gives you exactly I by pi, because you see minus I down is the same as plus I up. So it even gives you, so actually the coefficient of 1 over z prime is precisely what we want. If it was not precisely that, if it was some multiplicative factor, I just have to put that multiplicative factor also, right? But just in this case, just happened that I didn't need to put anything else. It's just as it is. So if I consider this function and integrate it with a 1 over 2 pi I, okay, then I would exactly reproduce these terms. So if I integrate it, now what should be the contour? Let's see. So I want to take a contour. So here is my 0, and then take a contour which is, so here is my 1, let's say. Take this contour like this, counterclockwise, and similarly here is minus 1, plus 1. Okay. So this contour I consider. Okay. I mean, again, you can take the sum up to some capital N. Okay. So then you have up to capital N. So you consider, so there is some capital N here. So you take a contour which encircles the first from 1 up to n. And similarly from minus 1 to minus n. Okay. And then take the limit n goes to infinity. Okay. Now, of course, this is fine. This is okay. But now the usefulness of this whole thing is that you should be able to deform the contour, right? So to deform the contour, I can consider this like what we did, I think, last time. This contour, I mean, this is a large circle, I mean semicircle here, and similarly here. Okay, so that the contour now will become that. I mean, you come here, come here, come here, then again come here, right, and like that. Okay, consider this big contour, right? But of course, you can do that provided you make sure that these integrals don't contribute, right? So let's see, so does it make sense? Well, this is true in this range. If theta is between 0 and pi, strictly between 0 and pi, this is indeed true, because let's see, I mean, up here in this part, e to the I pi z is exponentially suppressed, right? Because I mean, z is x plus iy, right? So you see, e to the power of I pi z is same as e to the I pi x times e to the minus pi y. Okay. Similarly, e to the I z theta is, if you substitute that, e to the I theta x, and then e to the minus theta y, right? So now look at this here in that range. In that region, y is positive and large, right? I mean, okay, basically it's large. I mean, in that case, so what happens? This is, both are exponentially suppressed. Okay, so this is exponentially suppressed, so I can ignore that compared to 1, right? But then there is this exponentially suppressed, right? So you can apply Jordan lemma here, and So that integral will not contribute in the large n limit, right? Because then the radius is becoming larger and larger, so it's exponential suppression. What happens if in the other limit here y is negative? You see, here the y is negative, so both of them exponentially blow up, right? So now I'll come here. This is much larger than that, so I can ignore 1. Okay. So then what is left over is, I mean, this is exponentially blowing, that's exponentially blowing, but this one is blowing more rapidly than that, because precisely because theta is in this range. You see, this is blowing up as e to the power of theta times modulus of y, right? Y is negative, whereas this is blowing up as e to the pi times modulus of y, and if theta is smaller than pi, see, this is going to blow much faster than that, right? So again, there is an exponential suppression. Okay. So therefore, I mean, this integral makes sense for theta in this range. Okay. So then you can just deform this contour. I mean, so this contour, I mean, it just is deformed. It just becomes a contour around here, because that's the only other singularity. There's no other singularity here for this function. You see, there's no other singularity. Only singularity is here. Now this is in the clockwise direction. You see, this when you deform, this is going to become clockwise. Okay. So all I need to do is to take this integral, integrate this expression around the origin in a clockwise. So I have to take care of that by putting an extra minus sign, right? But that just tells you that I should compute the residue at z equal to 0, right? But the residue at z equal to 0, I just have to look at the d minus 1 coefficient. See, at z equal to 0, this has no pole, because this is z equal to 0, this is 1 plus 1, 2, so there is no pole. This has no pole, so this is a first order pole. So all I have to do is just multiply by z and take z goes to 0 limit to find the residue. So this residue will just give me this is z equal to 0, this is nothing, and that is 1/2, right? But then it's a minus, because I have this clockwise direction. So you get -1/2, and that's exactly the answer. Yeah.
Why is it that when you deform the contour around, when it's going to around 0, you take the clockwise direction instead of counterclockwise?
Okay, let's see, before we go here, I mean, this was my original contour. Sorry, this is my original contour, right? Why you have to choose that contour? Because here, you see, my original integral contour was simply that, this one. This was just capturing the poles at odd integers here, right? Now here, it should be counterclockwise, right? If it was you could have chosen also clockwise, but then you should already put a minus sign here, right? But since I don't put a minus sign, I'm choosing a counterclockwise direction, right? Now I want to extend this contour to a big contour, right? But the orientation is this here, right? So, I mean, if I want to consider it as a contour like that, then it has to come here. So obviously it has to be in this arrow, right? And similarly, it comes here, it goes like that. So now you see it's one big contour, right? Now I start deforming this contour. Just take these 2 points and start moving these points here and bring this circle down, right? But in that process, this orientation is still the same here. This is clockwise orientation, right? So all I'm doing is that, given my original contour, I just deform it. No? And when I deform it, at the end, I find a clockwise contour at the origin. So that's why this -1/2. Okay. So this is, so you see that it's independent of theta. The residue is independent of theta, because at z equal to 0, it doesn't matter. Theta drops out. Right? Of course, that's because it's a first order pole. If it was a higher order pole at z equal to 0, you would have to expand it. In that case, theta dependence will appear. Huh? But here it was simply a first order pole. That's why. Okay. Now, what happens if, say, you are in this range? You see, in this range, you cannot use this. You cannot use that because, let's see, I mean, it will not exponentially be suppressed. This integral, I mean, these integrals will not vanish in that case. So let's see how. So suppose you are in this range. If you had just used this definition of the integral, it will not give you the correct answer, because let's take y positive. So let's go here, up here. Then this I can ignore compared to that, right? Because this is exponentially suppressed. So here denominator is just 1, but the numerator now you see theta is negative. So e to the minus theta y is positive, right? It blows up exponentially. So you cannot use that definition. However, you could use this here, minus I pi z. Okay. After all, this is not going to change anything apart from giving an extra minus sign. I mean, there are two ways of doing it. Either you do that, or already here in this expression, after all, I mean, so you want to change the sign here, either sign here or sign there, right? So one way is to change here, but if you then maybe it's easier to just change there, because after all, this expression is the same as just take m to minus m, because after all, I mean, summing over everything here, both positive and negative integers, right? So when I take m to minus m, you simply get here an extra minus sign because of this, right? So you get here minus I over pi m, and here you get e to the minus I m theta, right? M odd. The two expressions are the same. There's no difference between the two expressions, right? So it is more convenient to use this form. Okay. Why is it more convenient? Because now in this form, so if I want to get this residue, I mean this residue at m odd, here you see is e to the minus I m theta. So I must have e to the minus I z theta here at z equal to m. On top of it, there is an extra minus sign here compared to that. So I should have a minus sign here. Okay. So in this range, I will use this expression, and which is the same as that. Okay. I mean, this integral just gives you that as a residues. And now you see that the same thing holds like what the previous discussion. I mean, this in the range in the up here, this exponentially is suppressed. So there is 1 here, but this is also exponentially suppressed. For theta in this range, theta is negative, you see, right? So this is also exponentially suppressed. Okay. And similarly down here, this blows up, that also blows up, but since the modulus of theta is less than modulus of pi, this will blow up less rapidly than that, right? So there will be again exponential suppression. So once again you do the deformation, and again pick up the simple pole. At simple pole it doesn't matter because residual z equal to 0 here, so this sign doesn't matter. However, there's an extra minus sign here. So instead of minus half, you'll get plus half here. Okay. So that's I mean, there's an extra minus here, and then there's a minus sign coming from the fact that it is clockwise. So minus minus makes it plus. So that's how you get. I mean, so it's very crucial. I mean, you see, when you try to deform these contours, you have to make sure that whatever you do, it should be in such a way that these extra pieces don't contribute, right? If they contribute, then it's of it's not very useful. All this procedure, right? So kind of contour integral is useful when unwanted parts do not contribute, right? So that's the thing. And that was crucial. You see, without doing this, you will not pick up these opposite signs in these two cases. So it's a bit subtle, I mean, this thing. I don't know, I mean, last time there was also another example we studied. I mean, let's take another example now. I mean, okay, this was one. Is there any question here? I'll just take a few examples today to see how this works. In some sense, this is also a review of the contour integrals of the previous chapter. No? So, I mean, okay, any questions here? Now let's take another function, say f of theta. This will be continuous. I just take it to be continuous. It doesn't, I mean, you can choose, actually you can play with it. I mean, you can just start choosing various functions and try to work out the Fourier series and then try to see if you can do the inverse. No? Inverse meaning to getting the Fourier once you get the Fourier coefficient, you take the Fourier sum and see whether it reproduces the original function or it satisfies the theorem or not. You can just try. So just let me take another example. Suppose this is simply absolute value of theta. So therefore, if you try to draw it, so this will be like, so from 0 up to pi minus pi. So the function is simply that. Sorry, this, yeah, absolute value. Okay. So then I have to again compute. So let's compute Fm, which is 1 over root 2 pi, f theta, which is absolute value of theta, e to the minus I m theta d theta minus pi to pi. We can split this, I mean, so into minus pi to 0 and 0 to pi, which is same as 1 over root 2 pi, minus pi to 0, but in minus pi to 0, absolute value of theta is minus theta, right? Because when theta is negative, in this range theta is negative, so absolute value of theta is minus theta. So it's a minus theta e to the minus I m theta d theta, and in the then I have from 0 to pi, but in 0 to pi absolute value of theta is the same as theta, right? Because theta is positive, so it's theta. Okay. So let me just introduce. I mean, using a brief notation, let me write it like this: 0 to pi minus pi to 0, because the integrand is the same, right? Theta e to the minus I m theta d theta. I'm just writing in a shorter form, that's all. Because the integrand is the same, so I'm just taking this. Okay, so how do we do this integral? So I mean, again, integration by parts, nothing more. So write e to the minus I m theta as d by d theta of e to the minus I m theta divided by minus I m, right? And then do a integration by parts. So the first term, so theta e to the minus I m theta integral d theta will give me a boundary term, which will be 1 over minus I m theta e to the minus I m theta in whatever the boundary points are. And then I will get plus 1 over I m times the d by d theta hitting this theta, which gives you 1. And then I have just the integral to the minus I m theta d theta, which gives you again, so this whole thing is 1 over minus I m theta e to the minus I m theta with the appropriate, by this notation I mean, plug the boundary values, whatever the boundary values are. And here I will get again plus 1 over I m times minus I m e to the minus I m theta, but you can integrate directly, right? Again, the boundary values. Again, write this as that, and then just get the boundary values. Okay. So let's evaluate these things. So for example, let's look at the first term. So theta equal to pi and 0. So the first, this gives you, for the first part gives you pi, I mean there is a 1 over minus I m, okay, pi times e to the minus I m pi, which is minus 1 to the m, right? So minus 1 to the m. And then at theta equal to 0, it doesn't contribute because theta is 0. So that's the first one. Then at the second one, again theta equal to 0, there's a minus sign here, okay, and theta equal to 0 again doesn't contribute, but theta equal to minus pi will give you, okay, theta is minus pi, but this is a lower limit, right? It's a lower limit, so it's another minus, so it makes it plus. And then this evaluated at theta equal to minus pi which gives you minus pi times e to the power again minus 1 to the m. So this vanishes. So the first term vanishes because these two cancel. And the second term gives us, so first of all there is a 1 over m square from here. And again let's compute this. So the upper limit it gives you minus 1 to the m. Lower limit gives you 1. So this is minus 1 to the m minus 1 from the first bound integral. And from here you get a minus 1 again plus minus 1 to the m. Okay. So the full integral, I mean, so what the conclusion is, this is for m not equal to 0. I mean, this integral I have done for m not equal to 0. So this is equal to, for m not equal to 0, it's simply minus 2 over root 2 pi. I mean, there is a root 2 pi outside, which I have not taken into account yet. There is a root 2 pi. The factor of 2 because each of them comes with a factor of 2, right? And I've taken out a minus. So 1 minus minus 1 to the m divided by m square. This is for m not equal to 0. For m equal to 0, we can directly integrate. For m equal to 0, I mean, this just gives you, after all, this integral is simply the area of this. I mean, these two add up, right? There's a factor of 2. So for m equal to 0, you get a factor of 2. So 2 over root 2 pi. And then the area of this one here, which is 1/2 times pi square, right? Because I mean, this is theta. So at theta equal to pi, this is also pi here, right? So the height times this length divided by 2. So 1/2 pi square. And there is a factor of 2 because it's exactly the same area here also. Okay. So this is the coefficients. So now let's try. Is it? I mean, is there any question up to this? This is the. I mean, the straightforward calculations. The only problem that can happen is that some little algebraic mistake here or there, no? But yeah, okay. All right. So now we want to take this and and write down the Fourier series. So there is a I have to take 1 over root 2 pi times fm e to the im theta, right? This is what I have to do over all integers. So this is, let's first look at the f0 part. This is 1 over root 2 pi. So it's 1 over 2 pi. So 1 pi cancels. So there's a pi by 2. Is that correct? I mean, let's see if. So root 2 pi makes it 2 pi. So these 2 cancels and 1 pi cancels. So it's a pi by 2. And plus. Now this is, of course, this is vanishes for m even. And for odd m, you just get a factor of 2, right? So 2 times 2, 4. So there is a minus sign here. So minus 4 over 2 pi, because root 2 pi times root 2 pi is that. So that makes it 2 over pi. And then m square and e to the power of I m theta, where m is odd. Okay. Let's okay. So question is whether now this reproduces this this whole thing is actually becomes equal to that or not. In particular, let's look at, I mean, theta equal to 0 term. Theta equal to 0. So theta equal to 0. This simply is 1. So you get here m square odd. So sum over 1 over m square, where m is odd. Well, m positive and negative just gives you the same factor because m square is even, right? So it will give you another factor of 2. So 4. So 4 over pi at theta equal to 0. You get here pi by 2 minus 4 by pi 1 over m square, m greater than 0, m odd. That's what you get. And this should be equal to 0 according to the theorem, because the value of the function at theta equal to 0 is 0, right? So this should be 0. And similarly, let's look at theta equal to pi. At theta equal to pi, you find pi by 2 minus 4 over pi 1 over m square. But now I have a e to the I m pi, so there's a minus 1 to the m. So you get here minus 1 to the m, and m greater than 0 and m odd. Okay. And this should be equal to, according to this, it should be pi, right? Because the average value is the same, both are equal. So it should be just pi. Yeah. Well, actually, minus 1 to the m, in fact, you can see m is odd. So minus 1 to the m is anyway minus 1, right? So, I mean, anyway, the sum is over only m odd. Okay. So this is just a minus 1, so that makes it plus. Okay. Now, you see, these two are consistent. They at least are consistent, because if for this to be true, this must be equal to pi by 2, right? But then if you substitute that, pi by 2 plus pi by 2 is pi. So they are mutually consistent. Okay, but but I mean, more generally, one would like to check for any value of theta. Is it true? Is it true that I just get the absolute value of theta? So let's see again. Let's try to do the same type of tricks. We want to integrate this object, right? So we have to again construct some function which gives you a residue, which is that at z equal to odd. Z equal to odd integers. So so let's see. So as we said, for odd integers, I can just start with e to the I pi z plus 1, right? I mean, this will precisely be will blow up at z equal to odd integers. So we can do that. And then let's again take the range. So here, sorry, this okay, the picture was this here. The function is this here. This is pi minus pi. Okay. So let's again consider first theta strictly between 0 and pi. Theta equal to between. So I'm looking at this range here. Theta equal to 0 and pi. So I get this e to the I z theta and 1 over z square, right? Let's see what is the residue. We want to precisely pick up this factor, minus 4 by pi. Yeah? So at z equal to m, we said that this, you write z equal to m plus z prime. Then you get here 1 over m square from here. And then here this guy is minus I pi z prime, correct? Minus I pi, because when you write, there's e to the power of I pi m, but m is odd, so it's minus 1. I mean, it's only m equal to odd has a pole, otherwise it has no pole. So there's extra minus 1 here in that expression. And then from here you get e to the I m theta. Okay. Now if I want to get exactly this factor, okay, this is the I pi here. So if if I do a contour integral 1 over 2 pi I, what should be the extra number? I mean, those are crucial. That's why we need to work it out. So I need to get minus 4 pi minus. So I think it's just minus 4i. Is it correct? Let's see. Because if I multiply minus 4i, then minus I cancels, and you just get 4 over pi, right? Which is what that expression. No, I need plus 4i, right? Because there's a minus sign here. There's a minus sign here. Okay. I shouldn't get, sorry, not 4. To this, I should just get 2. 2. Correct? Because this is what I should get here. I mean, this is the expression for when looked at, I mean, I took here is m positive, but here is a full sum, m odd. So if I look at this expression as a minus, I want to get minus 2 by pi. And this will exactly give me, if I have a plus sign here, then 2i, so the I cancels, you get minus 2 by pi. Okay? So this is the integral I have to do. So once again, in the same situation, you have you integrate from, so here is 1, say, start from 1, minus 1, and all the way. And this is fine, right? Because for the same reason as before, this integral, I can extend this contour to make this big contour like that. Okay. And for like what I described before, because in this range theta between 0 and pi, there is no problem with this suppression, right? Because I mean, in the upper half part, this exponentially suppressed. So 1 is the dominant piece, so I can forget that. But this is also exponentially suppressed because theta is positive. Okay, and when in the lower part, this blows up, but that also blows up. This blows up faster than that in this range. Okay. So now I can. So this whole thing just boils down to computing this contour once I deform it. I mean, I'm going a bit faster because this is exactly the steps we did for the last integral. So now I have to take the residue of this at z equal to 0, but at z equal to 0 at second order pole, right? So I have to expand it because I have to pick up the d minus 1 coefficient at z equal to 0. So that will require a little bit of work. I mean, not too much, but let's see. So it will be so there's a 2i. There's a z square. All I need to do is expand it at z equal to 0, right? So if I look at the top one, it's 1 plus I z theta. And it's enough to expand up to first order because there is z square, right? 1 over z square. Next order z square will just give you a regular term, so we are not interested in that. So, and here you get 1 plus I pi z, but 1 plus 1 is 2, so 2 plus I pi z, okay, plus higher orders. Okay. So once again, I can take out a factor of 2 here. This becomes 1, but then I have here a factor of 2, a half. And now I can put it up by make a geometric series expansion, right? So this is the same as 2i, so I divided by z square, and you get here 1 plus I z theta plus dot dot dot, and 1 minus I pi by 2 z plus dot dot dot, because this is the denominator. When you make a geometric series, you get that. And then you multiply the two things, and we are looking at the coefficient of z. So this is same as, okay, I over z square, and you get here, multiply this out. So 1 plus the z term is I times theta minus pi by 2 times z, right, plus dot 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 plus order z square. So it's clear that the coefficient then is simply I times I, so minus. So this integral residue just gives me minus theta minus pi by 2. That's it, right? But I have to remember that I'm looking at the clockwise, right? So actually there's a plus sign. Now you notice when you substitute that here, this pi by 2 exactly cancels with that minus pi by 2, and you're left with simply theta. That's okay. Now if you want to do the other way around, I mean, so suppose I want to now look at the other region, theta between less than 0 and minus pi, then it's again better to write it as e to the minus I m theta, because after all I'm summing over m, take m to minus m, right? So this will become e to the minus I m theta. So there is a m, this remains the same, m square. So all it will happen is this, just put here e to the minus I z theta, right? And now again in this region the same these two integrals vanish. Okay. So what is going to happen here? All that will happen is that in this expansion this will become a minus sign, right? So this theta goes to minus theta basically. Huh? So here it's minus, and this theta becomes a minus, right? And then here it becomes minus. Okay. So substitute that here. Pi by 2 again cancels, but you get a minus theta, right? For theta negative, which means it's absolute value of theta. Okay. That's actually, I mean, it's already clear, this expression, this is even in theta, right? So it has to be absolute value of theta. Okay. So it's quite nice identities, you see. I mean, so what this is saying is that, for example, this equation is saying, so pi square by 8. So this is telling you that pi square divided by 8 is equal to sum over 1 over m square, m odd, m greater than 0 and m odd. It's, I mean, such kinds of formulas are quite interesting, because after all, remember, if you think about it, pi, what was pi? Pi was the ratio between the circumference of a circle divided by the diameter. Okay, it's some irrational number. I mean, say it's not a rational number; it's a irrational number, right? In general, but I mean, okay, one way to compute pi is just to measure. I mean, draw a circle, measure the circumference, and divide by the diameter. That will give you. But of course, I mean that there will be errors of the measurements, right? I mean, it cannot be 100% accurate. Right? But this formula, for example, if you just keep going to higher and higher m, I mean, you cannot do infinite sum, of course, but say take the first n terms, right? You sum it up, it will give you a pretty good approximation. Okay. To any desired level of accuracy, you can go up here. So without doing actual measurement, you can actually compute pi to any order of accuracy. No. I don't think there are probably better formulas for it. This is, I don't think it's very, I mean, a formula like that, in order to compute pi, would be useful if this starts converging very rapidly. No? I think there are other expressions. There are lots of identities. I think there are some other identities which converge much more rapidly than that. So those are more useful to actually compute. This is not very useful. I mean, for example, let's see, if I want to get an accuracy of the order of fourth decimal point, right, up to this accuracy, then I need to go up to m equal to 100, right? That's a lot. I mean, you have to sum 100 terms. That's a huge. You cannot. I mean. But there are other formulas which are much more rapidly convergent. So I mean, I just invite you to just take some function, and then just do the Fourier series and try to look back, try to go back to see if you reproduce if you satisfy the theorem, right? And in that process, you will also get a lot of review the second chapter thing, all these tricks with the contour integrals and so on. So it's useful. Okay. So now let me just do. I mean, so I think now I just move to the next topic. This won't be. This is still Fourier transform. Okay. It's not a Dirac delta function. So that's just a slight extension of this Fourier series. So idea is the following. I mean, here we always kept the interval minus pi to pi. Right, that was the interval, and this functions e to the I, the Fourier the modes, which was like e to the I m theta. What was the property they had? They had the property that this was periodic in this range, right? The value at pi, theta equal to pi, and theta equal to minus pi was equal. But suppose I had a, instead of minus pi to pi, suppose I have a range minus L to plus L, where L is any number. Okay. You can immediately extend this thing by the following way. To go from here to here, all I need to do is to scale pi to L, right? So I can construct periodic functions which are simply e to the I m over L times pi theta. So now theta is between this and this, okay? Not between, in fact, let me call it x, because usually theta we always think in terms of an angular variable, right? With a range minus pi to pi. So let me call it like this. So what we have done is that starting from here, I just replace theta equal to pi by Lx, which is exactly correct, because you see the end point x equal to L corresponds to theta equal to pi, and x equal to minus L corresponds to theta equal to minus pi. So just a simple substitution like that, and then the rest of it is exactly identical. Okay. So now the Fourier modes will be this, and here you had a 1 over root 2 pi, the normalization, to make it orthonormal. 1 over root 2 pi came because when you take the mod square of this, you get 1 over 2 pi, and mod square of that is 1, and the integral d theta from minus pi to pi was exactly 1, right? That's the reason why we chose root 2 pi, because the integral of d theta gives you 2 pi. You want to cancel that, right? But now the dx integral will give me, from minus L to L, will give me 2L, right? So if I want to get to normalize it, I should have 1 over root 2L, right? So that's the right. Okay. So now let's try to write the, so remember f of what is that? Yeah. So I mean, so now what we want to do, I mean, this is still, I want to start taking the limit L going to infinity. Okay. So I mean, this is now, L is arbitrary number, right? Now I try to take L to infinity limit. That is when you get Fourier transform, basically. Okay. So Fourier series is where you have a finite interval. I mean, everything is defined in a finite interval, and you are integrating, you are considering a Fourier series. But the Fourier transforms are obtained when you take the limit L going to L to infinity. Okay. So it's a full line, okay, full real line. So if L is going to go to infinity, we can rename, you see, I mean, you can call this whole thing m pi by L. Okay. This call this m pi by L st. Okay. Just call that. And delta t is simply pi by L. Yeah. So I mean, so what is happening as I change m? I mean, this is I mean, initially you have some sums, right? Sums over m's. Okay. So what is the difference between m and m plus 1? I mean, the one which comes with the m is that. Other one which comes with the m plus 1 is m pi by L x plus pi by Lx. Right. So in the large L limit, this is a very infinitesimal amount. It's a small, very, very small in the large L limit. So we call this as delta t. So I call this m pi by L as t, and this is delta t. Okay. Then this sum, the sum over m, can be replaced as an integral dt. Okay. I mean, after all, if you start considering such an object, e to the minus I dx times f of x, right? I mean, when you write in the Fourier series, how we wrote it? We wrote it f of x. I mean, instead of theta, I call it x now, e to the power of minus I m pi by L x summed over, integral over x dx. That gave us the Fourier coefficients m, fm, right? And then we consider the sum fm e to the power of I m pi by L x, right? This is supposed to give me back f of x, right? This is the Fourier series. But the summation is over m, right? But in the limit L goes to infinity, I can think of it as an integral, right? I mean, after all, if you just consider, plus itx, and let me call it f of t, okay? F of t. Suppose I want to consider this integral. If you try to use the Riemann definition of integral, what I will do, I will split this interval, the t interval, into infinitesimal amounts, which I call the infinitesimal amount delta t, and then sum it up, right? So this will exactly reduce to this sum here in the limit when L is very large, right? So that delta t is very small. Okay. So it's a natural thing to try. So first of all, this fm should be replaced by ft after all, because m plays the role of t up to some scaling, right? Okay, so this should be f of t. So a natural guess. I mean, this is not a proof. It's not a proof that we are taking that in some limit L goes to infinity, this Fourier series becomes Fourier transform. But what we are trying to do is to get some intuition from the Fourier series and start taking the limit L goes to infinity to figure out what kind of expressions we might expect. So then a natural thing that we are finding is that f of t, okay, this is the analog of fm, because m is basically playing the role of t. F of t is simply the integral f of x e to the power of minus I t x, okay, because m pi by L is t dx, interval minus infinity to plus infinity, and we'll again choose a normalization 1 over root 2 pi. Okay, that's that. And the inverse Fourier transform would be f of x. Okay, here is a question mark whether what it is. 1 over root 2 pi minus infinity to plus infinity f of t e to the I t x dt. Yeah. So again, repeat again. So the first equation is analog of this equation. Okay. All I'm saying is that because I'm treating m by L pi as t, I'm calling that as t. So this f which depends on m will give you something which depends on t, right? So I call that as a capital F of t. So f of t I define like this. Okay. And the second equation is analog of that Fourier series, because instead of f of m now is what we call is capital F of t, right? And this sum in the L goes to infinity limit should just become an integral, right? So you get here dt to the itx ft. Okay, again some 1 over root 2 pi factor. Okay, so this is what you would expect, that somehow Fourier series experience tells us that this is what we should expect in the limit L goes to infinity. Okay. But just like in the Fourier series, remember we quoted several theorems which essentially says that, I mean, if the function is reasonably well behaved, the original function is reasonably well behaved, you remember I think the conditions were it was a bounded variety, that it could be written as a sum of a non-increasing and a non-decreasing function, right? So you could allow discontinuity, but not too bad. I mean, some okay, for those functions we had some theorems. Similarly, there are some theorems for the Fourier transforms, and I will just again we won't discuss the proofs, but okay, let me just state the theorems. But before that, notice that Fourier transforms are much more symmetric, right? Here you see in the Fourier series, on the one side you have an integral, on the other side is a sum, right? Here it's essentially the same, you see, the two integrals, except for the sign change. So in other words, I mean, if this was true, suppose this was true, I mean, for some well-behaved function this would be true, Okay, if this was true, then okay, here this equation tells me that a capital F is a Fourier coefficient of Fourier transform of f of x, right? But if you look at this here, f of x is a Fourier transform of capital F of minus t, after all, just because of the flip of the sign here. So they are very symmetric. I mean, one of them is a Fourier transform of the other guy is a Fourier transform of the first one. Like, so it's they are symmetric. Whereas here it is not the same situation. On the one side you just have numbers, right? These are just some numbers. I mean, right? It's not a function of anything. It depends for fm, for each m is some number. Here, f of x on the other hand is a function in a finite interval. So this is much more symmetric. Okay, so let me just state the theorems without proofs, and then work out some example. So the statement is, so first theorem is the following, is, I mean this, okay, first of all, when you even write such expressions, we are assuming that this integral is well defined. I mean, it gives you some finite answer, no? So first statement is that if, so assume that that f(x) modulus is integrable, which means that the integral of this from minus infinity to plus infinity exists. This integral is well defined. So that's assumption. So I mean, let's just explicitly write down. Exists, which means less than infinity. Then of course this exists, right? Because I can take the norm of that and then use the fact that that's going to be less than or equal to the integral of the norm of this, but norm of this face is 1, so it's just the norm of that, but that we are saying exists. So ft exists. Okay, but now the question is, what about this here? Okay, and then the statement is that the okay, 1 over root 2 pi integral ft times e to the power of itx, okay, dt. I mean, of course, I mean, we don't know whether this, I mean, you have to define somehow this limit, right? So say minus lambda to plus lambda in the limit, and then we take the limit, lambda goes to infinity, okay. I mean, that is the same as, I mean, from minus infinity to plus infinity is the same as that. So first you do a finite integral, and then you take the limit, lambda goes to infinity. Then that's equal to average, half of f of x plus naught 0 plus f of x minus 0. So you see, even if f has some discontinuity, but it should be, I mean, so the left limit plus right limit, average of that. Okay, that's what this reproduces. Okay. I mean, in the notes it is written slightly in different way, because I mean ft is directly substituted. I mean, so one has substituted that, but apart from that, the same expression. Yeah, I mean, where ft is given by this ft is given by that expression. I mean, this exists by this assumption anyway. So that's the first theorem. And then there's another theorem which is probably even more useful for us somehow, in the sense of the Hilbert spaces and so on, I mean, quantum mechanics. This theorem again is not very symmetric, you see, in the sense that we are putting some condition on f of x, but basically nothing on capital F. No? All this tells you that f of t exists, but it doesn't tell you whether ft is integrable or not, no, etc. Yeah? But okay, this is giving you some theorem, some statement. But there is a more symmetric theorem. However, that is a bit less powerful in the sense that that is only in the sense of L2 spaces, which means those equalities will be almost everywhere type of equalities. Huh? Okay, so the second theorem is So the assumption is that f of t mod square is integrable. Fx dx is integrable. So that's the assumption. That means that f of x is in the L2 space, L2 with the weight function 1, L2 1, the L2 space. Then if you construct this function f of t lambda, which is simply given by the integral 1 over root 2 pi minus lambda to plus lambda, f of x e to the minus I dx, okay. Then the statement is that that this converges, okay, this converges, this as far as we take lambda to infinity. So this converges as lambda goes to infinity to some function f of t, okay. But it's a convergence again in the sense of L2 space. It converges to some function almost everywhere, f of t. That's one thing. Okay, it converges to some function f of t, whose such that this is also in the L2 space, okay, such that ft square mod square dt is also finite. Okay, so what we are saying is that we have this this limit. Each, I mean, for a finite lambda, of course, this is well defined. There's no problem. I mean, this exists, right? Okay. So the question is, what happens as I start taking lambda to infinity? Okay, lambda as I take lambda to infinity, the statement is that this converges to some function which is inside this L2 space, right? This is also mod square is again integrable. Okay, and furthermore, the inverse transform, again you define the same way, f of x lambda, which is f of t e to the I dx dt from minus lambda to plus lambda 1 over root 2 pi. Okay, this again as you take lambda to infinity, this again converges, and it converges to original f of x almost everywhere. It's always this theorem is every statement here is almost everywhere. Okay, so this converges, lambda goes to infinity to f of x almost everywhere. Okay, and furthermore, a very important, not important, a very useful relation is that, and furthermore, f of x mod square dx is equal to f of t mod square dt. This is like the Percival relation. No? See, the Percival relation was that, I mean, that if I had, I mean, this we are treating as some orthonormal basis. Okay, now it's a continuous, because this is t is not like Fourier series where you had a discrete set of, I mean, countable kind of thing. But just think of it as like it is providing a basis, right? Then these are the where is it? Yeah, then these are the like the Fourier coefficients, right? I mean, if I had an orthonormal basis, then this coefficient that I would compute will be the what we call Fn or something, right? And Percival relation was that the norm square of the original function is equal to the sum of the Fourier coefficient square. I mean the expansion coefficient square, which is exactly expansion. These are the expansion coefficients, and you take the square. That's the statement. Percival relation. I mean, usually you have Bessel inequality, right? But if you have a complete set of orthonormal vectors, then it becomes the equality, which is the Percival relation. Sorry? You mean, sorry, here? Okay, so this, no. As lambda goes to infinity, this converges to some function f of t in the L2 space, which what that means is that this is finite, this integral is finite. And furthermore, the inverse transform, so when you take the inverse transform, right, you keep it at, for a finite lambda, of course, this is some well defined, so you get a sequence of functions. For each lambda, you get a function. And this, as lambda goes to infinity, this converges in the mean to the original function f of x. Okay. That's what it's saying. Yeah.
For a given function, can we find the Fourier transform of that function?
Yeah.
For a given function.
I mean, for a function which, I mean, the integral must exist, right? Otherwise, it will not be, you cannot find, right? I mean, these integrals must be convergent. It should exist somehow, right? Okay. I mean, what this is saying is that if this is true, then all this follows. But already this may not be true for arbitrary function. Okay.
This is for convergence.
Yes.
For a given function, can we find are we able to find the Fourier transform of that function?
It depends on whether the integral makes sense. I mean, sometimes the integral will not be even defined, right? There must be some convergence property, because now the interval is infinity. Yeah? As x goes to infinity, you must have some, I mean, I do not know, for example, if some function f of x which is blowing up at infinity. There is no Fourier transform of that. Right. You should have some good behavior at infinity. Then, yeah, the Fourier transforms always exist. I mean, imagine there is take f of x as that, I mean, exponentially blowing up, x square. No? I mean, this will have no Fourier transforms. I think maybe I'll just consider some examples. I mean, this will have a problem, this kind of a function. I mean, if you try to integrate this into the x square times e to the I x t, this I wouldn't even know how to define this. I mean, this is exponentially blowing up at infinity.
We can put the factor 1 over 2 pi. We can normalize it. We cannot normalize it.
Yeah, we cannot normalize it. Yeah, correct. Yeah. I mean, yeah, this integral simply just blows up completely exponentially. Right. So yeah, I mean, you must have some. I mean, the function must have some good properties at infinity. I mean, so that you can integrate it. It should be defined. It should be well defined, the integrals. I mean, so here, of course, we have this condition. There's an L2 space, right? L2 from the full range, minus infinity to plus infinity. So this is already saying that, I mean, you have strong restrictions on this function f of x, right? For example, I mean, if a function f of x was 1 over square root of x, for example, it will not be satisfying, right? This will not be satisfied. So then it's okay. So let's consider some examples again. So one example here is okay. This we have already done, but okay, I think maybe it was even probably one of the problems if you're in the exam. I'm not sure. So consider f of x is 1 plus x squared. Okay. This is perfectly well behaved at x goes to infinity. This is perfectly, it's not exponentially suppressed, but it's sufficiently, it's power law suppressed, but it's enough for the integrals to make sense. Okay, so let's compute now f of t. This is 1 over root 2 pi f of x e to the minus I px dx from minus infinity to plus infinity, which is f of x is 1 over 1 plus x squared. So again, use the contour integral tricks, and we can find immediately the so we have to again take the two cases. I mean, so idea is to deform the contour, right? I mean, here is minus infinity to plus infinity, real axis, and then you, depending on the sign of this, you either close it like this or close it like that. So you have two cases. If t is positive, then to apply Jordan lemma, I need to close the contour like that. So in that case, the contour will become like this. This is for t positive. And for t negative, the contour will be this way. You will choose the upper contour for t negative to use the Jordan lemma. Otherwise, exponentially it will blow up. So you need to. So in the first case, so t greater than 0, you have this contour, and the poles are of course at plus I and minus I. I mean, if you replace x is equal to plus I or x equal to minus I, that's the pole. So you get this integral simply gives you 1 over root 2 pi. Now here it's clockwise, so I have a minus 2 pi I times this the residue at x equal to minus I. So that is what? X plus I times x minus I times e to the minus I tx. So you just take x equal to minus I, so this becomes minus 2i, and that becomes e to the minus t. Minus ti. Yeah, that's correct. Yeah, I think that's correct. Yeah. So that is for t greater than t positive, and for t negative, you have this contour. So you just get a 1 over root 2 pi times 2 pi I, because now there is no extra minus sign because it's counterclockwise. Okay, and the residue now is at x equal to I, so there is a 2i times e to the plus t. Right? This is for t less than 0. Notice that at t equal to 0, these two are equal actually, because I mean this minus minus cancels. So in fact, at t equal to 0, the two things are equal. So capital F of t is continuous at t equal to 0. Okay, so that is the expression, and now we can check if the inverse transform gives you back the same answer or not. Okay. So let's check that. So so now we want to check this integral f of t e to the power of I tx dt from minus infinity to plus infinity, the 1 over root 2 pi. Is it the same as the original function f of x or not? So I have to split this integral, of course, again in two domains, because I have two different functions, two different functional representations in two regions. So this gives you 1 over root 2 pi minus infinity to 0. So in this range, f of t is, so I can simplify this, right? I mean, I cancels as a 1/2 root 2 pi, but that root 2 pi cancels this, so I can just get rid of that. So it's get 1/2, and e to the t times e to the I tx dt. That is from minus infinity to plus infinity, and from 0 to infinity, minus infinity to 0, and from 0 to infinity, you have the same factor, 1 over 2, but now I have e to the minus t times e to the I tx dt. Yeah? Okay. So let's see. This is a trivial integral because this is just e to the t times 1 plus ix, right? And then when you integrate, so the first term gives you 1/2 of 1 plus ix times e to the t 1 plus ix in the two limits, 0 and minus infinity. And the second integral gives you plus 1 over ix minus 1 times e to the power of t times ix minus 1 from infinity to 0. Okay. So look at this one here. At t equal to minus infinity, this is exponentially suppressed. So the lower limit doesn't contribute here. only the upper limit contributes, but then t is equal to 0, so this is simply 1. Right? So the first integral, so first integral gives you 1 over 1 plus ix, and the second integral gives you the upper limit is 0 because at t equal to plus infinity, because e to the minus infinity, right? There's 0, and the lower limit gives you just 1, but there's a minus sign, so it becomes minus 1 over ix minus 1. Okay, I think I missed some minus sign. I don't know. I seem to have missed some minus sign somewhere. So you get so take this common factor. You get I can. Sorry, this is plus and 1 minus ix. Correct. No minus sign. That's what it is. So it's 1 plus x square, and then if you add that up, it gives you a factor of 2. I mean, ix cancels from the two ends, and this 1/2 cancels with that, and give you 1, which is the original answer. So inverse transform works. Now, in the last 10 minutes or so, let me take one more example. This function was a very good function. I mean, it's a nice function, completely continuous. There's no problem with this function. So when you have continuous function, original function is continuous function, and okay, it is sufficiently rapidly going to 0 at infinity, so that those integrals are all well defined, the inverse transform always gives you back the original function. However, let's consider now an example which is a bit discontinuous. Suppose I have a function which is just a kind of a step function. So f of x is equal to 0 for x less than minus 1, equal to 1 when x is greater than minus 1 and less than 1, and equal to 0 when x is greater than 1. This is x less than minus 1 all the way up to minus infinity. It's all 0. And this is x greater than 1 and all the way to plus infinity. So to draw the function is like this. So from minus 1 up to plus 1, the value of the function is this 1 here. And after that, the function is 0. Okay. Like that. This satisfies actually the conditions of both the theorems, right? The first theorem said that the modulus of f is integrable, and second was the modulus of f square was integrable. But the modulus of anyway, everywhere else it is 0, so this integral becomes finite integral, right? So it's satisfying both the conditions. Yeah. So let's see. So let's again compute f of t, which is 1 over root 2 pi minus infinity to plus infinity f of x e to the power of minus I tx dx. Okay. As I said, I mean, since f of x is 0 in this region, so effectively this integral just simply becomes minus 1 to 1, right? And there the f of x is 1, so it's just that. Okay. So this integral just gives me the 1 over root 2 pi 1 over minus I t e to the minus I t x evaluated between 1 and minus 1, okay, which is pi, and so there is a 1 over minus I t, and then this is e to the power of minus I t 1 x equal to 1 minus e to the power of x equal to minus 1, so I t. Okay, which is just 2i minus 2i, so 2 sine t over root 2 pi t. It's it's perfectly fine. I mean, one might have worried that there is a 1 over t here. At t equal to 0, it seems to have a problem, but there is a sine t here. So at t equal to 0, there is no singularity for capital F of t. Okay. So now the question is how whether we reproduce back the inverse transform is going to give you back that or not. So I take this expression. So we want to look at integral f of t. There's a 1 over root 2 pi e to the I dx dt. Okay. So you want to evaluate this integral to see if you get back this function. So this I mean at x equal to 0, this f of t is just that. Okay, and this integral we have already carried out in the second chapter. You remember? You remember we carried out this integral 0 to infinity sine x over x dx, right? And the answer was, I think it was pi by 2 or something like that. Huh? Okay, so for example, at x equal to 0, if I substitute all these things, there's a 2 pi makes it root 2 pi makes it 2 pi. So this becomes 1 over pi, right? I mean together with that 1 over pi, but this integrals from minus infinity to plus infinity. So since this is an even function, okay, so this guy simply becomes twice that. So that integral will give me a pi, but all the remaining part gives you 1 over, this gives you 1 over pi, so it gives you just a 1, right? Which is what you have at x equal to 0. This is 1. But one would like to see, I mean, that this should be independent of the value of x in between, right? Could be any point here, but it should be independent. So let's just check if how you get that, huh? How you get this result. Okay, so let's substitute this. Let's substitute this here. I mean, let me not use that form because it's more convenient to use this form because then exponentials you can multiply easily, right? So you get here, so 1 over 2 pi, and okay, let me take minus e to the it. So you get here I 1 over t, and then you get here e to the I t from here, and you get 1 plus x, one of them, and the other one will be so put here minus here t here minus e to the power of I t x minus 1 dt integral. Okay. Now, of course, at t equal to 0, there is no singularity because of this fact. I mean, this combines together to give you sine of t, and that factor at t equal to 0 just gives you 1. So there's no singularity. But I mean, what we would like, I don't know if you remember how we did this integral, sine t over t integral, right? It was a similar thing. There was no, I mean, we wrote sine of t as e to the it minus e to the minus it, okay? But then we want to take separately those things. So then, of course, I mean, this integral itself is not well defined at t equal to 0, right? Similarly, this integral is not well defined. Combined thing makes well defined. So what we did was we took this around 0. We consider put a cutoff here, some epsilon to minus epsilon, and there we put some cutoff r to minus r, and then we took the limit r goes to infinity and epsilon goes to 0, right? But at the intermediate step we did that. That is the reason why, I mean, this was not needed actually if we had kept this whole thing together, but we wanted to manipulate separately, okay? So we did this, and then we chose the contour like this, and like that, a small semicircle here. Okay, so let's do that and see. But now together with this x, see, before in the previous calculation there was no x. Now I have to keep track of x. Okay. So we have to consider various regions. So let's suppose x. Maybe I should try to. write it in a different way. So this in the second integral, let me just exchange t with minus t. Let's redefine t to minus t. Okay, I mean it's not necessary, but okay. So that integral becomes 1 over 2 pi I e to the power of I t times 1 plus x minus or okay. So if I have to consider different regions. So let's consider the region where x is I mean in the region where it is 1, right? So x is less than 1 and greater than minus 1 in this region. So I mean this guy is always positive, right? But this guy is always negative in this region, right? In this range, x minus 1 is always negative, right? So I will change this t to minus t in the second one, right? So that it will become again positive. So now what I have is plus e to the power of minus it, so plus it times 1 minus x. Okay. This is plus. Okay, I'll explain why. Okay. When I change t to minus t, the dt by t remains invariant. Okay. However, the limits change, right? I mean, this limits for minus r to minus epsilon plus epsilon to r. Okay. So the limit changes. So for example, let's do it here. Minus infinity becomes plus infinity, and that becomes minus infinity when I take t to minus t. But then I can put it back by removing the sign here. Okay? So plus that, and so now it's so all of these things. So I will still write minus infinity plus infinity, but it's understood that I really mean this part with epsilon. This is a shorthand notation for that, but should be understood. Okay. So now you see both these coefficients are positive. Okay. So I can deform the contour up. Use Jordan lemma. Right? Do that, and so that part will not contribute, and then the whole thing was. I mean, we have this integral. Consider this big contour going from here and then up like that, right? The integral of this whole thing, of course, is 0 because it has no pole. If you look at this integrand, inside this inside this half disk, there is no pole. I mean, the only pole is at t equal to 0, but t equal to 0 is not included there. Not there. So therefore, I mean, the total answer is 0 in that if you integrate over the full contour. So that means, but on the other hand, this part of the integral doesn't contribute. So what this is saying is that this integral plus that integral should be equal to minus of this integral, right? Because I mean, this integral plus that integral is 0. Okay, so this plus that should be equal to minus of that integral, but minus of that integral. I mean, this is clockwise, so it makes it counterclockwise. So therefore, this integral is just the integral 1 over 2 pi I in the epsilon semicircle and clockwise. Of the sum of the two terms, e to the I t 1 plus x plus e to the I t 1 minus x over t dt. Okay. But in that semicircle, t is epsilon times e to the I theta, right? Where theta goes from 0 to pi. No, but as I said, I mean, this integral plus that integral is minus of that integral. So now I'm saying this integral is equal to minus of that integral, which is the same as the counterclockwise. Right? So this guy becomes epsilon e to the I theta I d theta. This is epsilon e to the I theta, and I just have to expand. So epsilon cancels. Okay, e to the I theta also cancels. And this integral is from 0 to pi. Okay, and now I can just, since epsilon is very small, I can expand. I mean, t is epsilon. So, and all the higher terms are going to just be suppressed in epsilon. So, leading term is 1 plus 1, 2. So, you get here 2 times I times pi, 2 pi I, which cancels with the 2 pi I and gives you 1. Okay. So, that was in this range. Okay. Now, so let's see what's the difference here. I mean, if I had taken x greater than 1, okay, if I take x greater than 1, I shouldn't change this. I shouldn't redefine t to minus t, because this is positive and that's positive. Both are positive. Okay. So I just take this function and go through this thing. Jordan lemma tells me that part of the integral doesn't contribute for x greater than 1. Okay. So like once again, this plus that becomes equal to this integral counterclockwise. But now each of them, when you do the same expansion, you see, so now what's the difference? Here you have a minus sign, and here you have x minus 1, right? But in any case, I mean, this didn't matter because we just look at the leading term, right? But the leading term 1, 1 with a minus sign cancels. So you get the answer 0. Okay. Similarly, if you have chosen x less than 1, then you see both are negative, right? So you should do this trick t to minus t on both the things, or you close the contour down, because both are negative. So you can choose to close the contour down, and instead of choosing this, you choose that. Okay. Once again, there is no pole inside. Okay. But the relative sign is minus, so when you expand it in the gamma epsilon circle, they cancel. Leading term cancels. So once again, you get 0. Right? Is that clear? I mean, no. Which part? You agree with this first part? Huh?
Yeah,
this part you agree.
the last one, when you place t equal epsilon e for I theta.
T equal to epsilon. So yeah, so this was simply epsilon e to the I theta. This is epsilon e to the I theta. I times d theta. I mean dt is epsilon e to the I theta I dt d theta. And here again, I just replace this epsilon e to the I theta. Wherever you see t, you are replacing by that. But now you remember at the end, I'm going to take the limit epsilon goes to 0. So at this stage, this cancel already. So this part is independent of epsilon. Right? Here it depends on epsilon. So since epsilon is small, I can make a Taylor expansion of this each of these terms. So the first term gives me 1 plus I epsilon e to the I theta 1 plus x plus order epsilon square, right? Similarly, the second term gives me 1 plus I epsilon e to the I theta 1 minus x plus order epsilon square. That's the second term, right? But the point here is that, I mean, actually only the first term is important because we want to find something which is doesn't vanish in the limit epsilon goes to 0, right? So there's just 1 plus 1. Because all the other integrals are finite integrals anyway, right? So, yeah, I mean, see, there could have been subtlety if these integrals were blowing up. When you integrate over theta, this somehow the integral was infinite. In that case, you cannot ignore the epsilon terms, right? But here the integrals are all finite, right? So it's just going to be epsilon times some number, finite number. So if the limit epsilon goes to 0, it vanishes. So the whole difference between this region and that region and that region is this relative sign. Okay, something you arrange it so that these coefficients are positive, right? The coefficient which comes with the IT is positive, right? And once you have arranged that positive, then the whole issue is whether this is plus or minus. If it is plus, these two add up, these two ones add up. If it is minus, they cancel. If you take, yeah, I mean, so, yeah, in fact, it was not so important. I mean, you could have also, I mean, here I changed in this region, I changed the t to minus t, right? But really you don't need to do that actually. I mean, you could just take, I mean, in this region what is said, this is positive and that's negative, right? So for this guy you choose this contour, and for this guy you can choose that bottom contour, you know. I mean, but then again you have to keep track of all the signs and so on, so I thought it's easier, I mean, so that everything is just choosing one contour, right? Because then you have to keep track of all these various clockwise, counterclockwise signs and so on, you have to worry about it. And because here you see the cancellations or adding is happening between these two terms, right? So if you make some mistake in some sign, you will have, I mean, you'll get totally wrong answer. So that's why it is better to keep as one integrand with one particular contour, so that it's easier to control signs. No? That's the reason.